Hello everyone, this is ML Naruto. Welcome to my channel. So today I'll be explaining the topic regarding the shrinkage methods. So we have few techniques in this shrinkage methods. So I'll be explaining why do we need these shrinkage methods and uh, what is the use case here and all the things under the math behind those concepts and all the things. Okay. So but before that, I want to tell you something like. Okay. So this is my data set and this y is nothing but my dependent variable. All right. So these are all my independent variables, that is x1, px2, px3, x4 and so on. Okay. So there are so many independent variables but only one dependent variable. Okay. This will be the usual scenario, whatever maybe the data set is. So this is our data set. Okay. So, but yeah, what happens is when you try to build any kind of machine learning model, you'll often use these existing independent variables, and using these existing variables, you try to build, you try to create a separate additional variable, right? For example, here I have x1, x2, x3, x4. Okay, these are all my independent variables. Okay, so I often thought that if I want to improve my model accuracy, then what should I need to do? I need to do some kind of feature engineering, right? So I need to perform some kind of feature engineering. So how to do that? So that actually depends upon the particular data set, right? So let's imagine I want to create any kind of new variable. So how would I create? For example, I will get some kind of new variable, that is x5. If I try to multiply x1, sorry, if I want to add x1 plus x2, and if I use this output as a new variable, that is x5, so this would be the scenario here. So I can do that. X5 is my new variable and it is created using x1 plus x2, right? If I add these two variables, that is x1 and x2 here, I'll get new variable, that is x5. So what should I do now? So what happens is, here I'll be having some other column, that is x5, right? Let's imagine this is my new variable, that is x5, and this will be my dependent variable, that is y. Okay, so these are all my independent variables. But what happens when you try to when you perform some feature engineering here, and what happens? You'll end up having more number of features here. See here, earlier we used to have only four columns as our independent variables. Okay, only one column as our dependent variable, that is y. But what happens when you try to perform some feature engineering? You'll end up having five columns instead of these four columns. You have you'll end up having five columns here. So what is this? What do you mean by this here? Whenever you will get more number of columns, there may be a chance that if your data points are less, for example, if you have the data points, okay, that is rows. If you have rows that is very less in number, okay, you have very less number of rows, but you are actually creating more and more number of features using this feature engineering. And what happens when you do that? Your columns, that is your features, will grow more. That is uh, very much. So columns, you have too many columns, okay, so you can, so you will have too many columns but very less number of rows, then what happens? What's the output of this situation? This situation will end up creating the impact of curse of dimensionality. I have already explained you in my previous video. What do you mean by this curse of dimensionality? If any of you haven't watched this yet, I'll request you to watch that video. I'll be putting this link of that video in my description in the I button also. You just have a look at it. Okay. So if you have very less number of rows and high number of columns, then this situation will end up creating the curse of dimensionality. So what happens when you have the curse of dimensionality? I have already explained there. So your model won't be in a stable condition. It would be suffering with the variance error, or you can call it as a risky model. So you won't rely on this particular model, which is suffering with this curse of dimensionality. So this would be the impact of the curse of dimensionality, right? So this would be I mean, we would be having this kind of situation if we try to perform this feature engineering concept, right? If you try to perform feature engineering, you'll end up creating many more columns. Okay, so this feature engineering concept is actually leading to the curse of dimensionality. Okay, so uh, this is one kind of a scenario, and another scenario is another scenario is oh, sorry. So yeah, so feature engineering leads to that curse of dimensionality. So if you want to encounter that, right? So you want to tackle that problem. You want to tackle that, but how? Using two methods. For that, for in order to encounter that particular curse of dimensionality situation, you'll use we use regularization, regularization techniques or methods, whatever you call. Both are same. Okay, so we use regularization techniques. So first one is nothing but the ridge regularization, and the second one is lasso regularization, right? So now I'll explain what is meant by these two regularization methods, right? But before that, if you want to understand these two terms, you need to you just need to recall what we have discussed earlier. So that's nothing but yi minus beta minus sigma j equal to 1 to p beta j into xij whole square, and all these things are sum up I equal to 1 to n. So this what do you mean by this equation? Earlier we have already discussed this particular equation. This equation is nothing but linear regression cost function, right? So this is the linear regression cost function. Did you get that? So linear regression cost function. This entire expression is in the form of yi minus y hat whole square, right? So see here, this is the entire thing yi, right? So this is the intercept here, beta naught is the intercept, and this is the variables, that is y hat. This is our predicted variable, and this is the coefficient of that particular corresponding variables, right? So we are actually squaring the entire thing. So this is in the form of yi minus y hat whole square. Did you get that? So this is nothing but the linear regression cost function. Okay. So what do you mean by this y hat here? So y hat is nothing but mx plus c, right? So if you try to substitute that thing in the y hat, so what happens? yi minus mx plus c. Okay. So what is meant by this yi here? So this is yi minus. So what is meant by this mx? So here m is nothing but slope, right? So that is nothing but beta j. Okay. And what is meant by this x here? So x is nothing but xij, right? Plus c. What is meant by the c here? C is nothing but the beta naught, right? So beta naught. Did you get that? So just now compute this v yi minus what happens? Uh, Beta j into xij, uh, sorry, minus beta naught. So this is the equation for our linear regression, right? Did you get that? And now we are squaring it here, right? So this is the same equation. This is the same equation as this, right? And now we are just squaring it, and this is the entire thing for which we call linear regression cost function, right? So that's the thing here. So, but this is the linear regression cost function. But now we are actually dealing with the regularization techniques, that is RIZ and Lasso. When we want to talk about this particular first thing, that is RIZ. So what is the basic difference between this RIZ regularization method and this linear regression cost function? So I'll be explaining that. So we have already seen that what is meant by linear regression cost function. Now I'll be explaining you what is a ridge regression. Okay, so for that you need for your linear regression cost function. So if this is the linear regression cost function, for this cost function you'll be adding some kind of other term, right? Additional term. You'll be adding some additional term to our existed linear regression cost function. Then this entire expression together makes a ridge regression, right? So what's that? I'll tell you. Don't worry. So what do you mean by this linear regression cost function? Earlier we have already discussed yi minus beta naught minus sigma j equal to 1 to n, sorry, 1 to p here, and beta j into xij. This is the whole square, right? And here we will be having the sum of it. So I equal to 1 to n. So this is the linear regression cost function, right? Now this is the plus. This plus symbol is as is. And now this additional term is nothing but the lambda lambda into sigma j equal to 1 to p beta j square. So this is the additional term, right? Did you get that? This is the additional term here. So together that makes a ridge regression. Did you get that? So I'll be explaining. So what is the meaning of this lambda and what is the meaning of this beta j square and all the things I'll be explaining. Just hold for a second. Okay. Okay, but I want you to know something like what is the basic functionality of the linear regression cost function and this ridge regression? So what is the basic functionality here? See, in our linear regression, what is our agenda here? We need to find the best fit surface, right? So this would be the x-axis, this would be the y-axis, right? And we need to, here we will have some kind of points like this. Okay, we need to find the best fit line. Okay, so we will call uh, we will call something a best fit line or a best fit surface, right? When your independent variable is having only, when you have only one independent variable and one dependent variable, this would be your best fit line, right? But what if you have multiple features, that is this is x1, this is x2, and this is x3, and you have one dependent variable, that is y. Then you will have the data points like this. Okay, then that surface, we will not call that surface as the best fit line, but we will call that surface as the best fit plane or best fit hyperplane or best fit parabola, you can call it as. Why? Because the shape will lie like this, maybe here like this. Okay, so it will forms like a it will form like a it will form some bowl like a shape, right? So for that shape, this shape is having some kind of parabolic shape. You can call it as a parabolic shape. Okay, so you will get this particular best fit line when you only have the two features, that one is independent, one is dependent. And this kind of a shape you will get whenever you have multiple independent variables. See here, you have three independent variables and only one dependent variables, right? So this is the scenario here. But what is the purpose of this best fit line? Finding the best fit line here. Best fit line is the is that line for which yi minus y hat, that is the actual minus the predicted one. The difference between the actual and the predicted one would be very low. When you get that difference, then we call that line which gives us this low sum of squared error, when you call that line as the best fit line. Did you get that? See here, this is nothing but the sum of squared error. Sum of squared error. Best fit line is that line which gives the low sum of squared error, and we call that line as the best fit line. Similarly, here also, this particular parabolic, right? This is the best parabolic shape. Okay, best parabolic shape. We call any shape as the best parabolic shape if it gives us the difference between the actual and the predicted, that is the sum of the squared error, as very low. That is low sum of squared error, low SSE we can call, right? So any shape that gives low SSE, we call that shape as the best parabolic shape, right? So okay, so the agenda is very pretty much clear here. Like whenever the linear regression, whenever we run the linear regression, the agenda would be like this. We need to find the best fit line, right? So, but here, what is that particular additional term which is actually making some kind of difference between this linear regression uh, and this ridge regression? So, what is that? That is nothing but this particular term, that is the lambda here. Okay, the term is like a penalty term. You can call it as a penalty term. Why are we actually calling the penalty? So, what is mean by a penalty here? When you do any kind of uh, when there is something wrong, right? Uh, some government or some governing body will usually uh, have some kind of penalty, right? So penalty is nothing but there is some kind of wrong and you need to penalize that. So what is meant by this penalize? Penalize is nothing but you, there is some, I'll explain. See, there is some kind of wrong is happening. Okay, there is something which is wrong is actually happening, and you are actually trying to penalize it. Penalize is nothing but you're trying to make the things correct, right? Whenever there is some kind of wrong is happening, you're trying to make it right. You're trying to make it right, right? So if you try to penalize something, you will try to get the things right, right? So that's the meaning here. Penalize means that's the meaning. So here, what is the what is the uh, I mean, what is the use of this particular penalty term, that is the lambda here? Okay, so for that I need to draw something for which you can understand it better. Okay, so okay, so we have already discussed this thing. Okay, so you have the data like this. Okay, you have the data like this, and now see here, the gap between each of those data points is very huge, right? There is some huge gap between those data points. So our algorithm will get confused and it will draw. I mean, it doesn't know what kind of shape to be drawn in this particular surface. So it will get confused and it will try to assume that okay, uh, let's proceed with the simple straight lines. Okay, so it will just uh, continue its progress with these simple straight lines here. Okay, okay. So likewise, the algorithm will try to draw some kind of lines, simple straight lines, right? So what happens here? See, just observe the angle here. So let's imagine this is the x-axis. Okay, okay. I'm just taking my x-axis here. So if you try to observe the angle here, there is a sharp angle, right? So when you just look at the angle here, there is again a sharp angle. And when you just try to observe the angle here, there is a sharp angle. So what happens is your algorithm will get confused and it just started applying all the simple straight lines, and it has already fit these straight lines over your data. Okay. So see here, just observe the 1 minute. Okay, so just observe here. Uh, did you observe these heavy angles here? So these are the sharp angles here. So why do we actually occur these kind of sharp angles here? Why? Because earlier I have already told, when you perform feature engineering, that means whenever your data set has too many features, okay, whenever your data set has too many features but very less data points. Okay, this point is very important, but very less data points here. So what happens? Your algorithm will try to fit these simple straight lines on your data set, on your data especially. Okay. So due to that reason, you'll be having some, sharp peaks and sharp valleys kind of shapes. So if you have sharp peaks and sharp valleys in your data set, then automatically you will be having some sharp angles here. That is the sharp slopes here. The slope is very much sharp. So okay, we already have sharp slopes. So what does that mean? So what happens when we have sharp slopes, right? So if the model has sharp slopes, then automatically our model will fall into overfit scenario or overfit zone, right? Whenever our model has these kind of sharp slopes or sharp kind of peaks and sharp valleys, then our model will definitely fall into this overfit zone. But you can ask me that I mean, what's the relation between them? What happens when you have sharp peaks, and why does our model will fall into that particular overfit zone? You can ask me. See here, the slope here is very much sharp, right? When you say the slope is very much sharp, then after when you try to evaluate your model, or when you try to perform modeling, then what happens is you will get some kind of coefficients, right? So you will get some kind of coefficients. Those coefficients will be extreme, either extreme positive, right, or either they or they extreme negative. That means they will have their values. I mean, they have the values with huge magnitude. That is huge magnitude. Either it is the huge positive magnitude, or either it is a huge negative magnitude, whatever may be that, but they will definitely have this huge magnitude here, right? So they'll have this huge magnitude here. So yes. So due to that reason, what happens is our model can't have this property of explainability. That is, you can't explain our model. This would be our risky model. This would be the unstable model. So what happens? Our model will perform. Okay. When you have higher magnitude, then what happens? Our model will perform. Our model will perform well on the on trained data. Okay, but whenever an unseen data has come, or whenever a test data, or whenever a production data, that is unseen data, is fit to our model, then it will perform poor on the test data, right? So this scenario is known as this overfit. This scenario is the overfit scenario. So for this reason, we need to reduce those sharp peaks and valleys. So in general, I'll tell you, see, previously we have these kind of shapes, right? Right. Earlier we have these kind of sharp peaks and valleys, right? This is the slope here. This is the slope. This is the slope. This is the slope again. So we need to make those sharp peaks and valleys as the smooth slopes. So how to do that? So I need to make so I need to make like this. Okay. So what happens now? The slope has been reduced. See here, the slope has been reduced. The slope has been reduced. Then ultimately our coefficients, that is the magnitude, then ultimately when the slopes are reduced, our magnitude of our coefficients will also be reduced, then what happens? Our model will give the same results on both the train data and the test data. That is, it will perform very well on the train data, and it will also perform very well on the test data. So this is the scenario which we can consider it as best fit scenario. This is the best fit. This is neither a overfit or an underfit. Okay, but this is the best fit scenario. Why? Because our model is actually performing very well on the train data, and it's also performing very well on the test data. So the ultimate agenda here is to uh, we have this sharp kind of peaks and valleys. Now we need to smoothen them. Okay, so how to smoothen them? How to perform smoothing here? So how to do that? How to smoothen those sharp peaks and valleys? You need to perform we we do smoothing. We do smoothing of those sharp peaks and valleys using what? Using the penalty term, that is the lambda here. Okay, that lambda is that lambda plays a crucial role in smoothing those curves. Okay, so that lambda plays a very big role in smoothing those curves here. What is that lambda here? I have already told you that this is the lambda. Which one? Where is that? See here, this is the lambda. Did you see here? This is the lambda, which is used to smoothen those kind of sharp peaks and valleys here. See, these are the sharp peaks and valleys here. We need to smoothen them as this kind of shape. Okay. Why are we actually smoothing here? Why? Because if we try to smoothen these kind of sharp peaks and valleys, you will get the magnitude of the coefficients will also be reduced. What happens when the magnitude of the coefficients will reduce? Then our model will perform very well on the train data, and it will also perform very well on the test data. That means it would be in a best fit scenario. So how to smoothen these kind of a curve here? For that we need to have one penalty term, that is known as this lambda. Did you get that now? I hope everything is pretty much clear. Okay. So I want you to know one certain thing, that is this lambda here. Uh, Besides smoothening this curve, it also reduces the sum of the squared error. Right? Did you get the point here? Why? Because here, see here, see here. Earlier we have this kind of a sharp. See, earlier we have this kind of sharp peaks and sharp valleys, right? So here, what happens is the sum of squared error will be very low. That is, at times sum of square error will become 0. Okay. Then what happens if sum of squared error is 0? Then every point, then if, for example, if sum of squared error is 0, then there is no difference between the actual and the predicted one. That means our model will exactly predict the actual data like this. Did you get that? If there is some kind of difference between the actual and predicted one, then what happens? Our model will predict like this. Did you get that? See, every point is not actually on the same particular plane here. Why? Because there is actually some kind of difference. When you have some kind of difference between the actual and the predicted one, then this would be the scenario. But when you have uh, when there is no difference between the actual and predicted one, that is when SSE is equal to 0, then this would be the scenario here, right? So obviously it will definitely do well on the train data, but it will obviously fail on the test data because the test data is unseen here. Did you get that? Okay. So now we have got to know that lambda is used to smoothen this particular sharp peaks and valleys here. Okay, so what should be the value of the lambda here? I want you to know. What happens if I set my lambda value as 0? Okay, if I set my lambda value as 0, that is, what is meant by this 0? 0 is nothing but the low. Then what happens? What happens? The coefficients become as in the linear regression equation. Did you get that? That is, if there is no lambda, I mean, if I'm not actually using any, lambda is 0 means what? The impact of lambda is 0. That means, see here, I'll tell you. See, this is the diagram, right? This is having the sharp peaks and valleys. Okay, if I want to smoothen the curve, smoothen these sharp peaks and valleys like this, I need to use the lambda. But if I am saying that my lambda is 0, that means I'm not actually using my lambda. Okay, then if I won't use the lambda here, then what happens? Will I be getting this kind of shape? No, the shape would be like this only, right? If I don't use the lambda here, my shape would be like this only. Okay, but if I try to give some kind of value, then what happens here? If lambda equal to, I'm providing, if my lambda is some kind of value, that is, if my lambda is high, okay, if I'm giving the lambda as the higher value, then what happens? Coefficients are highly suppressed, right? What do you mean by this suppression here? What do you mean by the suppression here? Suppression is nothing but, see, I'll tell you. See, this is the earlier sharp peaks and valleys, right? What if you have, see, if you use lambda equal to 0 value, then what happens? This would be the shape here. Then you will get this kind of a shape. There is no change in this previous shape. Why? Because there is no impact of this lambda value. That is, lambda equal to, we are saying lambda equal to 0. That means we are saying that there is no impact of lambda on this particular figure here. That means you will only get this kind of a shape. There would be no smoothening here, right? Then what happens? Coefficients remain as it is. As it is. Then obviously this particular situation is the overfit situation, right? So obviously now also you will get this overfit situation only. Okay. What happens if lambda equal to high? That means I'm saying lambda value is, I'm setting my lambda value as too much high, right? Then what happens? This peaks and values will be smoothened like this. See here, is there any kind of a slope here? No. Why? Because this particular curve has been smoothened like this, right? So this is a situation where our coefficients are smoothened. Our coefficients are smoothened highly. Or you can also use this particular term like suppressed. Okay, our coefficients are suppressed. What is meant by this coefficient here? Coefficient is nothing but the slope, right? This slope angle, all the slope angles are suppressed highly. Then what would be the scenario you will get? Then you will get the situation that is the underfit. That means at this particular data, on this particular data, our model would be underfit. Why? Because this data won't be working on the trained data. This data, I mean, our model will perform poorly on the trained data, and it will also perform worstly on our unseen data, that is test data. So we don't want this kind of a situation, and we don't want this kind of a situation. We want a situation like this. See here, this, we need this kind of a situation. That is, we neither want overfit or underfit, but we want best fit. What is the best fit here? So for a I mean, for a figure like this, that is the sharp, for a figure that is having sharp peaks and valleys like this, we need to smoothen them like this. Okay, so now just observe here, the slope has been reduced, right? The slope has been reduced here. Just imagine here. And the peaks also has been reduced, right? So we need this kind of a smoothened curve. This situation is known as the best fit situation. This is neither a overfit or an underfit. Okay, this is neither an overfit or an nor an underfit, but this is the best fit scenario. Here we need to know, we need to find, we need to find that best value for our lambda, that is our penalty term. Okay, what would be the value of lambda if you if our model to be in this best fit scenario? That means if we want just to smoothen this particular sharp peaks and values a bit normal, so what would be the value of the lambda? That's what we need to find that. Okay, did you get that? I hope I'm pretty much clear. So what I'm saying is, if you have this kind of a situation, that is, if you have sharp peaks and valleys, then uh, our sum of squared error would become zero. That means our model will usually perform well on the trained data, but it won't be performing well on the unseen data. Then you will end up having poor results for your test data, which is a overfit scenario. But what if the lambda value is too high? Then it will usually suppresses this particular sharp peaks and valleys very highly by forming this kind of a shapes here. See the shapes here. Is there any slope here? No. Absolutely, there would be no shape. Why? Because the lambda value is damn high. Due to that, all our coefficients are actually get suppressed. Then the result would be our model will perform poorly on the trained data, and it will also continues its poor form on the test data as well. This situation is known as this underfit situation. We neither want we don't want neither of this we don't want either of these situations, either overfit or underfit. No, we don't want. We only want this best fit situation where those sharp peaks and valleys are slightly suppressed. We are just slightly reducing the coefficients here, right? If we are reducing the coefficient slightly, then that shape or that particular model will give us the best fit model. That means this particular model will usually works better on the trained data. It will also continues its good form on the test data as well. This would be the best fit model. But we need to find the best value for our lambda. Okay. This particular situation is actually depends upon this particular uh, lambda value. Did you get that? So this kind of a model will usually generalize better. Okay. So yes, okay. This is the situation here. Now to I want to show something here. I want to show something actually. So just look at this picture here. So just look at this picture here. What did you observe here? These are the coefficients for the simple linear regression model of 10 dimensions, right? So earlier I have only 10 columns. Did you get that? Earlier, I only have some 10 columns, but after performing feature engineering, I'll end up having some 57 columns. See here, coefficients with the polynomial features. I have already used polynomial features here. Then what happens? These 10 dimensions have become 57 dimensions. That means initially I have 10 columns here, but after performing my feature engineering using polynomial features, I have some 57 features here. These are all the coefficients of those 57 features here, right? And now just look at the magnitude here. What is the highest coefficient here? Just look at it. 2.53. Okay, this is the highest, I think. No, not this. Maybe 2.93. Yeah. So this 2.93. Wait a minute. See here. What is the highest value in this entire coefficients? This particular 2.93 thing is the highest, right? And what is the lowest value here? That is this minus, right? Minus 5.5 something is the lowest here. Okay, so the coefficients range is lying between minus 5.5 to 2.93. Okay, this is the range initially when we have only 10 columns. Okay, but now after performing our polynomial features, look at the range here. What is the range here? What's the range here? See, the range is actually different, right? So the range is actually different. See, just observe all the coefficients which are having e to the power of 12, e to the power of 10, e to the power of 11, etc. These are all the coefficients which is having some huge magnitude. Okay, these are having some huge magnitude. Did you get that? What is the meaning of this huge magnitude? That means our data is in the form of sharp peaks and sharp valleys here, like this. Okay, our data is like this. So the slope is very high. That means the coefficients are actually very high here. Did you get that? So this is the result of it. If you ever observe e to the power of some huge number, that is usually we'll be facing some e to the power of 1 or e to the power of 2 or something like this, but here e to the power of 10, 11, 12 means, that means these coefficients are having huge magnitude, right? That means the data is like this is an overfit scenario. We need to use some regularized models, either RIDS or Lasso. Then only you will get the regularized models here, for which we need to choose the lambda value. Did you get that? This is some kind of an example. I have taken this picture as an example, right? Okay, okay. So now, so yes, I'm just clearing all the drawings here. Okay, so this is the scenario of using the ridge regression. Okay, that's the scenario of using ridge regression. Now, what is something special about the lasso regression here? So I want to tell something about lasso regression now. Earlier, what I have explained everything regarding ridge regression. Okay, now this time I'll be explaining something about lasso regression. So what is the equation for this lasso regression here? Similar, very much similar. Earlier I equal to 1 to n here. Okay, there I equal to 1 to n. Here I equal to 1 to m here. The equation is same. Yi minus sigma j equal to 0 to p here, and wj into uh, wj into xij. Okay, wj into xij whole square plus we need to have some uh, additional penalty term, that is the lambda here, and after that lambda into we have some sigma equal to j equal to 0 to p, and after this we have mod. Okay, we have mod wj. Okay, so this is the additional term. This is the linear regression. This is the linear regression cost function. Okay, for that linear regression cost function, we are actually adding some additional term, that is plus lambda into sigma j equal to 0 to p mod wj. Okay, earlier we have observed that there is some kind of earlier when you observe the difference between this particular equation and the previous equation is somewhat almost similar, but that additional part was having some kind of difference here. See here. See here. See the additional part here. This is our linear regression cost function. Okay. And this additional term, when you observe additional term, here we are actually squaring up the coefficients here. Okay. We are actually squaring up the coefficients using we are actually squaring up the coefficients, and we are actually summing up, right? Summing up all those things, and we are actually penalizing all this output. Okay, finally we are actually using lambda to penalize this entire output. Did you get that? But what happens here? But what's happening here? Here we are not squaring up the coefficients here. Instead, we are actually taking the mod here. Okay, this is the basic difference. Here we are actually taking the mod. We are not squaring up the coefficients here. Did you get that? So lasso regression is very much similar to the Ritz regression, but with a small difference, that is in terms of the penalty term here, right? So the penalty term, what we are actually using this as the wj. Okay, so actually lambda is the penalty here, and uh, this is the input for our penalty. Okay, the input for our penalty would be here wj. Wj is nothing but see, whenever you say wj, it is actually rising to the power of 1, right? So you can also, this is also known as this L1 norm. Okay, it is also known as this L1 norm. Okay, so the term is an input value which decides how high penalties would be for the coefficients. That is, larger the value, more diminished the coefficient is. For example, see, I'll explain. If lambda is high, okay, if lambda is high, then then coefficients are highly suppressed. Are highly suppressed. Okay, so larger the magnitude of the coefficients, lambda should be the higher value. For example, if you have this wj, right? If you have this particular wj, if it is having some kind of huge value, then lambda should also be huge, right? For example, if wj is huge, then lambda value should be huge. Then only it will get suppressed, right? So here, unlike the ridge regression, where the coefficients are driven towards the zero, okay, the basic difference between the Lasso and ridge regression, I will tell you now. Okay, so earlier this is the Lasso part, okay, and now this is the ridge part. Sorry, confused. Earlier I have explained the ridge here, ridge regression. Now I am explaining the Lasso here. What is the basic difference here? What is the basic part of difference here? Okay, earlier, unlike the ridge regression where the coefficients are driven towards the zero but may not become zero, Lasso regression penalty process, I'll tell you. Earlier, what happens is all the coefficients will be will be driving towards 0. That means we have our lambda value. This lambda value is trying our coefficients to become 0. Okay, it will try to make our coefficient 0, but coefficients won't be 0, but coefficients won't become 0 in this case. Okay, our lambda will try hard to make our coefficient 0, but the coefficients won't become 0. In which case? In this ridge regression case. Okay, but now here in the lasso regression part, what happens is lambda will try to make our coefficients 0, right? And all our coefficients will become 0 here. Okay, this is the basic difference here. All our coefficients will become, not all our, uh, some of our coefficients will become definitely 0. And what happens after they become 0? What happens after they become 0? So after the coefficients become 0, so we will drop. Sorry, sir, not we, actually. So our algorithm, okay, so our algorithm will drop those values. Will drop those columns which has 0 coefficients. Did you get that? If you don't get, no worries. I'm here to teach you all the concepts here. See, just focus here. Here I'm saying coefficient will be driving towards the 0 using what? Lambda. So here in the ridge regression part here, lambda will be trying very hard to make our coefficient 0. But the result would be the all our, but our coefficients won't become 0. Okay, even after hard trying of our lambda to make the coefficient 0, but our coefficients won't never become 0 in ridge regression. But here in the lasso regression, our lambda will try hard to make our coefficient 0, and the result would be some of our coefficients will definitely become 0, right? Then what happens after becoming all our some of our coefficients has become 0? Okay, now what's the process here? What should we do now after they become 0? What happens if any coefficient is 0? Means that particular column is having no value. So why do we consider that particular column in our machine learning model? So we should not consider that particular column. So that's the reason why would we choose to drop those columns for which we have 0 coefficients. I'll explain. Okay, so so this is our linear regression model, right? This is our linear regression model. This is our x and this is our y. So this would be our straight line, best fit line. Okay, this is our model. So when I say model, what is this? This is nothing but the y equal to mx plus c, right? And now if I try to project this particular x-axis here in a dotted line manner, so this would be my slope here, right? This would be the slope here. So earlier I'll be having some kind of slope. That means I will be having m equal to some value. I have m as some I have some value as my slope, that is m. Okay, that means that particular column is having some kind of importance. If slope is having some kind of value, then that column is having some kind of value, right? But here if we use the lambda here, but if we use this lambda in the lasso regression here, what happens is this particular line will become parallel to the x-axis. That means this particular line will become parallel to the x-axis. Then what is the slope here? There is no kind of slope. Why? Because it is actually parallel to the x-axis, right? This is x and this is y, and this is our y equal to mx plus c. Here, what is the value of m here? M equal to 0. Why? Because is there any kind of angle here? No. You should never look for this particular thing here. I'll tell you. See, is there any angle between this particular two? No. Why? Because these two are actually parallel here. So that's the reason. That's the reason for which m is equal to 0. M is equal to 0 means coefficient has become 0 now. Okay, if any coefficient has become 0, then what happens? Then the column, for which coefficient is 0 is having no value in model building. Okay, so if we have any kind of column, see, I'll tell you, we have some, let's say x1, x2, x3. These are all our independent variables. That is our columns, and y is our dependent variable. Okay, let's imagine I have got the coefficient value x1 equal to plus 2 point something, 2.1, and x2 equal to, let's say 0.56. Okay, but x3 equal to, I have got the value as 0. Then I can say that x1 is very much important to me. Why? Because it is having the higher value, that is plus 2.1, and x2 is also somewhat important for me. Why? Because it is also having some kind of value, that is 0.6. Okay, but x3 is not important for me. Why? Because it's having 0 value. That means it doesn't have any kind of value. So how can I consider this in my model building? So I won't be considering this in my model building. So what can I choose to do now? So my algorithm will drop that column. So my algorithm will drop that column which has 0 coefficient, which has 0 as the coefficient. Did you get that? So this would be the scenario here. Why are we actually dropping? Okay, this is the mathematical terms, but why are we actually dropping here? See here. Here, if there is, here we are actually saying the slope is 0. That means there is no relationship between x and y, right? If slope is 0, then x and y are not related with each other. That means it has some 0 correlation, right? It doesn't have any correlation with our y. So if this particular x variable is not a good predictor of y, then how the heck do we consider it in our machine learning model building? So we usually drop them, right? But on behalf of us, our algorithm is actually doing that particular job. See here, my algorithm will drop that column which has 0 as the coefficient, right? So lasso regression is actually doing that job here. But when I want to talk about this particular kind of pros and cons of this model, that is the lasso regression or the ridge regression here, I'll tell you. See here, Lasso. Okay. See, what is it actually doing? Yeah, it is actually, if any slope is 0, then it drops the column, right? It drops the column, which is insignificant in machine learning model building. But we do the same kind of thing, right? We do the same kind of thing. We can also do the same kind of thing. We can also drop the columns in the data frame before model building. If we found that there is some kind of insignificant in the data, right? When we try to see the data, this is our data, right? So this is our data, and when we have noticed that some column is of insignificant, right? Let's imagine this is x1, x2, x3, and we have found that x1 is of no use. X1 is of no use. So what we can do? We can simply drop x1 column from our data frame, right? So we can also do this particular job, right? Before building the model. So uh, so this is the thing here. So this particular algorithm is of not much use. Why? Because we can also simply just do that particular job. We can also drop those columns if we found them insignificant in machine learning model building, right? So but lasso regression is often used as a feature selection technique. Okay. And in the real world scenarios, we hardly find any kind of simple linear regression models. Okay. We oftenly see, I mean, we oftenly use Lasso, and we usually use Lasso and the ridge regression models only. We won't be using any simple linear regression models or multi-linear regression models. Okay, we won't be using any of these kind of things in the real world scenario. We will only be using, I mean, in the most cases, we will only be using Lasso and the ridge regression only. Do you get that? So this is it all about Lasso and the ridge regression part here. I hope you have got some real good amount of clarity. Okay. So this is what I have explained to you today. Okay. So yes, this is the part of Lasso and the linear regression. Okay, I have already explained you the terminologies here, and I have already explained you the main concept. Why do we need this particular Lasso and ridge regression here? Why? Because we are actually prone to the curse of dimensionality here, right? So if your data is actually facing curse of dimensionality, then uh, Lasso and ridge regression would be one of such methods for which we can encounter this curse of dimensionality. Okay. So when you try to look at this particular equation here, this would be our usual equation, that is linear regression cost function. Okay. But here, what is the basic difference for between those two? We are actually adding some additional terms. Okay, additional term, that is the lambda and this particular beta j square. That is, we are actually squaring up the coefficient parameters, and also we need to reduce that using lambda here. Okay, I have explained the ridge regression, and now this is the diagrammatical explanation, and I have already explained I have already explained, sorry, I have already explained this lasso regression part here. Okay, and finally I have told you that this is the basic sorry, this is the basic difference. Okay, the basic difference here is in this ridge regression, in this ridge regression, all our coefficients, I mean, our lambda, that is our penalty term, will try to make all our coefficients zero, but all our coefficients won't become zero in ridge regression. But here in lasso, our lambda will try to make all our coefficients zero, but the result would be some of our coefficients will definitely become zero here. So our algorithm will drop these columns which has 0 coefficients. Okay. For this particular point here, I have explained it diagrammatically. Okay. And then finally, we can also do the same kind of thing what a lasso regression will usually do with the help of before model building. We usually drop certain columns which we found, if we found them are insignificant in machine learning model building, right? So this is the use case. This is the usage of the regularization models here. Okay, so that's all for this video. I'll see you in the next video, and in the next video I'll be explaining the error functions, uh, using some kind of contour graphs. Okay, so there I'll be explaining the uh, real real math involved and behind this region lasso regression and all the other cost functions. Okay, so I'll see you in the next video. So that's all for this. Bye bye, take care, Jai Hind.